This is ASFurther Pure Maths. We're on Unit 4 looking at vectors, and we're still on 4.8 applications of the vector product. The last video we were finding the area of a triangle using the vector product, and we're going to look a wee bit just here at volumes and see what we can come up with. So volume of a parallelepiped, so that's like a kind of a squashed box if you want to think about it, or you can kind of parallelograms here and they're kind of stretched up then at angles, whatever way you want to think about this. Volume of a parallelepiped is given by the area of the base, which is this bit, times the perpendicular height. Hopefully that makes sense, which is times h, where h is the perpendicular distance between the base and the top face. In the parallelepiped above, O is the origin, and A, B and C have position vectors A, B and C. So coming out of O, which is our origin, we're going to have A, B and C. The base of the parallelepiped is a parallelogram. That's nice and straightforward. And obviously the parallelogram is just two triangles. So remember the area of a triangle was half times the vector product. Then the area of the base here is just going to be the vector product. Okay, so if OBC is a half OBC, blah, 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 you should know the opposite angles of parallelogram are equal in size. Therefore ODBC is a parallelogram. That's okay. So effectively, that's your B, that's your C. So the area of this is then just simply going to be B cross C, and that's what these lines here are taking you through. So the volume of a parallelepiped is therefore B cross C times by H. Sorry, you can't see that. B cross C times by H. Now let's take a wee look at H. So there's our H, and if we make a wee right angle triangle there, where that's phi, and if you want then that's going to be our another angle. So we have an H and we have an A. So that's effectively the hypotenuse, that's the adjacent. So we can write cos phi is H over OA. That means H is OA cos phi, where phi is the angle between the vertical and OA. So there's the vertical and there's OA. So H is OA cos phi, and that means the volume then is B cross C times OA cos phi, because it was B times C H. So that's B cross C. So that's going to be magnitude of B cross C, magnitude of A times cos phi, or if you want then just changing those two around, A, B cross C cos phi. But B cross C is vertically up in the direction of H, since B cross C is perpendicular to both B and C. Of course it is. So phi is the angle between A and B cross C, and magnitude of A times magnitude of B cross C cos phi is the scalar product of A and B cross C. Thus the volume of a parallelepiped is given by A dot B cross C, which is usually written without the brackets because there can be no confusion, as simply A dot B cross C. This quantity is usually known then as the triple scalar product. So we had a great way of working out our vector product, and that was to do I, J, K, first vector, second vector. Evaluating the scalar triple product, you can run through here and kind of see where it's coming from, but effectively it's nice and straightforward. You replace the I, the J and the K with the A values, A, A1, A2, A3, and then you just find your determinant as before, and that gets you the triple scalar product, which then is going to be actually your volume of the parallelepiped. It's nice and straightforward. You'll see an example in a second. Next one then to move on to is volume of a tetrahedron. Effectively a tetrahedron is a sixth of the volume of that same parallelepiped. And so we can kind of sort of prove that if you want. So it's going to be a third times the area of the base times H. So the area of the base is obviously half of the area of the base of the parallelepiped. So it's a half times a third of that. So we end up then with a sixth, A dot B cross C. So let's take a wee example, and hopefully it might make a bit more sense then if we're working in there. A tetrahedron has vertices at, find the area of the triangle relative to find the volume of the tetrahedron. Sorry, there's been a bit of a problem here tonight, so let's get rid of that. So a tetrahedron has vertices at here, here, here and here relative to the origin O. Find the volume of the tetrahedron. So if we draw out a wee vague tetrahedron here and see if we can work out what's going on. A dotted line going across there, and if I call it A, B, C and D, and we have some point O. So the distance then from O to A is 0, 1, 0, and then to B is that, sorry, not the distance, but you know the kind of coordinates how to get from there to there. So we're going to take our A as our base point and find out the vector AC, AB, and AD. So AB is obviously going to be, how do we get from A to B? Minus OA plus OB, so it's OB minus OA. So it's that, take away that, so it's going to give us 1, 0, 2. Then AC is going to be obviously OC, take away OA. So it's this, take away this, so it's going to be then minus 2, 1 and 1, 0, 3 and 0, 3. And then AD is O to D minus O to A, 2 and 0, so that's a 2, 0 minus 1, 1, and we end up then with that. So our volume then is going to be a sixth of A dot B cross C. Now, if we were asked to find the volume of a parallelepiped, so that should say a sixth. Seriously, how confusing. That's a sixth. If we were asked to find the volume of a parallelepiped, there would be no sixth there, and we just do this and just do that sum, and then that works it out for us. So, as I said in the previous one, we drop the I, J, and the K on the top of that one. So, if we find the determinant, so instead of I, J, and K here, I'm putting 1, 0, and 2. They're coming from here. And then minus 2, 0, and 3, 2, minus 1, and 1. So our volume then is going to be a sixth. 1 upon 3, I think. Minus 0 upon who cares. Plus 2. That's 2. And live with that. So we're going to have a 3 here and a 4 here. So it's a 6 times 7. And so our volume is simply 7 over 6. Just another wee bit then about the triple scalar product. You should notice that sometimes when you're using the triple scalar product to evaluate the volume, the answer is negative. This is because when you evaluate the vector product to find the area of the base of the figure, you may unwittingly evaluate the product in reverse order. That is, you work out C cross B instead of B cross C. The result is therefore a vector pointing in the opposite direction to the perpendicular height of the figure. You should remember from the previous stuff, so obviously not page 210, just from the book that this is taken from, that C cross B equals minus B cross C. This is what causes the answer to be negative. Under these circumstances, the answer you require is the modulus of the triple scalar product. It's a fancy way of saying just drop the minus, and then that'll give you the right answer.